Deepen Pharmaceuticals in association with Higher Secondary Principals Forum.
Now here is another important case which I have defined using inverse trigonometric function. See the form here, it is y equal to e raised to sine inverse of 2x. So if you ask me what kind of function have I taken for differentiation, I would say it is again a composite function. But I very well see that this composite function is formed by combining exponential form, inverse trigonometric function, and there is a polynomial form taken. So therefore, if I have to write the derivative of this, I have to have the knowledge of all my formulas, exponential form, inverse trigonometric form as well as polynomial form. So when I write the derivative of this expression, the value dy by dx, so therefore I am differentiating the expression with respect to x. I go in the sequence, I read the function as e raised to, so the first function in the sequence being exponential function. And since we very well, so therefore I know that I have to tackle three parts. Remember, the first part will be the derivative of exponential part. Second in the sequence will be the derivative of inverse trigonometric function. And third in the sequence will be the derivative of the third function, as you see, is 2x. See, there is no confusion at all because I know that there are three functions in sequence. So the derivative also has to go in the same manner. So when I am filling the first part here, I know that I am writing the derivative of exponential form. And I have already learned that the derivative of exponential form is always the same. So with respect to exponential form, the derivative will be the same function. So e raised to sine inverse of 2x has gone into the first bracket. Done with this, now in the sequence comes the inverse trigonometric function. Which inverse trigonometric function? Sine inverse. What is the derivative of sine inverse? We know is 1 upon root 1 minus x square. But I know that I have to use the formula for sine inverse of 2x. So as per the identity, now the derivative will be 1 upon root 1 minus not x square, but in this case will be 2x the whole square. And then in sequence, I multiply this by the derivative of the third function which I have identified, the derivative of 2x, which I know is 2. Done. So the major differentiation part is over. What I just can try then is just settling the term correctly, so therefore I may then combine them, the whole form together, and may write the final answer as this. So the value of dy by dx finally is equal to this. So followed, how exactly do we have to use the knowledge, of differentiation of inverse trigonometric function? We may try another important case here. Say for instance, I am given y equal to e raised to x into tan inverse of x. Now see, the form has changed now. What is my value of y? How does it looks? I have y equal to e raised to x, one function, given multiplied to the function tan inverse of x. So what I am given looks like the product. So it is a product of two functions. I know that I have to differentiate product form. And if it is the differentiation of product form, I cannot do away without using product rule. That's it. So therefore, when I am differentiating this with respect to x, dy by dx has to be using the product rule. So therefore, so it is always that you recognize the form well, understand the form well, and there always you have this proper method suggested to you, taught to you previously of differentiation. So if I identify this as the product form, I know that I very well have this product rule to apply for differentiation. I use the same. So I have the first function into the second function. The derivative will be the first function to be kept same. To this we multiply the derivative of the second function. I have learned that the derivative of tan inverse of x is 1 upon 1 plus x square. The product rule tells me this is plus the second function, that is tan inverse of x, into the derivative of the first function. The first function being exponential function, the derivative is the same. And this has therefore helped me in finding the value of dy by dx. Next, what is next in the concept differentiation of inverse trigonometric function is that There are also some cases wherein differentiation becomes easy when we make use of all some of the important trigonometric identities which we have learnt in standard 11. So therefore, let us now take few examples wherein you will find that the differentiation of inverse trigonometric function, no doubt, but you know the differentiation process becomes easy when you make use of these trigonometric identities. Say for instance, I have one case. Say for instance, I find that the example given is y equal to cos inverse of 2x square minus 1, and it is given to find the value of dy by dx. Now what I will do is, when I will look at this particular example, I will certainly know that I am given to differentiate inverse trigonometric function. But now the thing which will come into my mind, will I now try finding the derivative of this by using the same old trigonometric identity which I have derived, differentiation identity which I have derived, or is there any simple other method that I can try here? So now here we are talking about the simple other method. And what is the simple other method? I am talking about all trigonometric identities, how they can be skillfully used here in making differentiation easy. So for that reason, it will be very essential for us to go back to the trigonometric identities. Now which identities? The relevant one which I can use here. Now see that I have the form y equal to cos inverse of 2x square minus 1 given for differentiation. What I will do therefore is, I will try to make use of some substitution in place of the variable x. The form is defined in terms of x. I am given to find dy by dx, no doubt, but what I will do is, just to make the process of differentiation easy, I would here prefer replacing the variable x by some other variable. Now how do I do that, or how do I select that other variable? It would be all the knowledge of trigonometric identities which help me in knowing which particular proper substitution will I have to try here. I know that there is one identity of trigonometry which is defined in this manner. It says that cos 2 theta is equal to 2 cos square theta minus 1. Now why selecting this particular identity? It is because if I just compare the term which is in the bracket here, 2x square minus 1, if we just see, it is exactly going in this particular manner. It is exactly in the form 2 cos square theta minus 1. So I want this particular term to be written as 2 cos square theta minus 1. And obviously, if I want this particular term to be written as 2 cos square theta minus 1, obviously what has to go in place of x is cos theta. See, how did I get to know about this? It is the trigonometric identity which has helped me in knowing this. I compared it very well with the trigonometric identity, and that is how I rightly tracked that this is the particular function which has to go in place of x. I would try substituting this in place of x. So therefore here in the solution part, my value of y now will become cos inverse bracket 2 cos square theta minus 1. I got the right thing which I wanted actually to come inside the bracket. And therefore, see how the work therefore becomes easy now, it has become easy now in the next step. So the value of y now can be written as cos inverse bracket. I know very well that 2 cos square theta minus 1 is nothing but the formula or the identity for cos 2 theta. Let me use the same here. I have used the form. It is the knowledge of inverse trigonometric function which has therefore helped me in knowing that my value of y therefore is equal to 2 theta. So it is the knowledge of inverse trigonometric function which has helped me in reducing this particular expression to this form. So therefore the earlier value of y, which was all in terms of inverse trigonometric functions, see, it has become the way we have simplified it. The new value of y now is the simple form 2 theta for differentiation. But don't forget that this has to be differentiated now with respect to x, because the question asked is to find dy by dx. What therefore I would try doing is, I will therefore replace theta in terms of x again. How do I do that? I know that x is given, we have taken x equal to cos theta. This therefore will enable me to write the value of theta as cos inverse of x. And if it is so, I would therefore now at this particular level prefer replacing theta by the value cos inverse of x. Just compare the new form that you have obtained for y. It is, let me tell you, in all, we have just tried to simplify the given value of y using the substitution method. This was the form given for differentiation, was looking bit complex. We tried using the substitution, and it is this particular substitution which has therefore helped us in simplifying the given expression of y. Compare the original form with the new form. See the simple form which we have managed converting it into. And if you look at the new form, I would say this is the easiest form that we can have for differentiation. What is the new value of y? Y is equal to 2 cos inverse of x. And now your actual process of differentiation will go in. Since the question is to find dy by dx, it is here at this particular level that I would differentiate the equation with respect to x. And therefore, when differentiated, the value of dy by dx therefore will be equal to 2 into derivative of cos inverse of x. As we have learned or derived, the derivative of cos inverse x is minus 1 upon root 1 minus x square. And therefore, we finally obtain the value of dy by dx as minus 2 upon root 1 minus x square. So, here are the set of examples, okay. So, therefore, you may try some more examples of this kind, but remember that this concept talks about finding the derivative of inverse trigonometric function, but by simplifying the form rightly by using the right trigonometric identity and then taking up the concept of differentiation. So, the differentiation all will happen somewhere towards the end, but the first major part would be on simplifying the given form by using the right trigonometric identity. So, in a sequence, next in the topic is something called as logarithmic differentiation. Now, if I just have to brief you all on this particular concept. Now, see again a technique which is used for simplifying the process of differentiation, what we can summarize it all in a way. Meaning, if there are certain forms given for differentiation and if you cannot skillfully handle them by using all the old identities of differentiation which we have learned so far, then you can always use this important tool. What I will say is logarithmic tool for simplifying, for helping you all in simplifying the process of differentiation. That is how I will summarize it. So, therefore, let us see the cases today wherein the difference you all will understand or find, you will see that the process of differentiation becomes easy when you take the application of logarithmic function. So, in this particular concept, just to brief you all, in fact, like we have combined or brought together all those cases wherein you will notice that the process of differentiation will become easy when we take the application of log. So, therefore, let us case by case see or get exposed to these kind of examples. Now, just to make you all understand in a better way, let me just here write some cases here for you for differentiation. Say the first function given for differentiation is defined as x raised to 9. Say I have second function given for differentiation and is defined as 9 raised to x, and say I take the third function for differentiation which is defined as x raised to x. Now, if you ask me all the three forms, all three are in the form of exponents. See the first case, I have y equal to x raised to 9. The question, no doubt, in all the three cases is to find the value of dy by dx. So, if I try to tackle the first case, I see that though it is an exponent, it is defined in the form x raised to 9. So, to make it, to elaborate it in a more better way, I would say the function is in the form variable raised to constant number. So, it is variable raised to constant number, and if it is variable raised to constant number, I do not know how to write the derivative of this. There is an identity helping me in writing the derivative of this function. What is the derivative? As we know, derivative of x raised to n is always n x raised to n minus 1. And so, this allows me to write the derivative of x raised to 9 therefore as 9 x raised to 8. I could easily tackle this particular part. I had no difficulty at all in writing the derivative. First part is over. Coming to the second form, again an exponent, y equal to 9 raised to x. Again, as we are proceeding, just don't forget comparing the second case with the earlier case. So, now again an exponent, but if you see place wise, I have placed them exactly the other way around. Meaning, if you ask me what is the form taken, it is constant number raised to the variable. Earlier, it was variable raised to constant and we had the answer for this case. Now we have a constant number raised to the variable. How do I write the answer for this? Dy by dx. Again, if you just recollect, then you will notice that there is a formula helping us also in writing the derivative of this term. Which formula? Derivative of a raised to x. What is the derivative of a raised to x? We know that derivative of a raised to x is a raised to x into log of a. So this has again made my work easy here. Derivative of 9 raised to x accordingly is 9 raised to x into log of 9. I could also tackle this part easily. So therefore both these sections are completed. We could easily write the derivative for these two cases. But now coming to the third case. Now if I ask you to compare the third function with the earlier two defined, then definitely there won't be any difficulty for you all in understanding that though the component, the exponent, I haven't used any constant as such in defining the term. In the sense, the form, if I say the form taken for differentiation is of the form variable raised to variable. Now please recollect, so far in whatever section that we have completed of the topic differentiation, we never ever had come across this kind of situation. So it is for the first time we are coming across the case wherein we are given the difference to differentiate variable raised to variable form. And if it is variable raised to variable, we know very well that we do not have any identity for differentiating this particular expression. And if there is no identity for differentiating this particular expression, no reason to panic. But remember that I would therefore make use of this important tool. I would prefer calling it as a tool, handy tool for overcoming this difficult situation that we have come across. What is that handy tool? It is nothing but application of log function. And it is today now let us understand how exactly this important tool, logarithmic tools, helps us also in overcoming these kind of situations. The form precisely, it is variable raised to variable form. So now this explanation must have made you all clear when to take help of this log tool. It is only when you come across the case defined as variable raised to variable. So let me try to explain this to you by means of one example. Say the case given for differentiation is x raised to sine x. If I read the function, also make it a habit of course always of reading the form, because when you read the function you get to know how exactly it is defined. So I read it as x raised to sine x. So I have variable x repeated at both the places, variable raised to variable, variable raised to variable. And if it is variable raised to variable, then always to click for this application of log. So therefore what I will therefore do is, I will take the application of log on both the sides of this equation. So therefore in a real sense, when I apply log on both the sides of this equation, it will therefore enable me to write the equation as log y equal to log of x raised to sine x. And therefore here I would therefore make use of one important property of logarithm. What is that important property of logarithm? You all know the property well, but just helping you all in recollecting. It is therefore log y equal to, it is log x whole raised to sine x, and if I just try to write the identity here for you, we know very well that log of a raised to b can be written equal to b into log a. This is one of the important property of logarithm which works. And therefore if I now try to use the same here, so if I have log of x raised to sine x, the knowledge of this property therefore will allow me to write the expression as sine x into log x, isn't it? So it is this sine x which has come here, followed by the function which we had at the base. So therefore it is now sine x into log x. I would now say that we are now at the level which is very easy for differentiation. The differentiation we noticed was quite difficult here because the form was variable raised to variable, but it is this application of log function has helped us in simplifying the complex form. We now have a simple form for differentiation, and now if you know very well that the form for differentiation is now a simple form, let us therefore immediately take up the differentiation part. Differentiate the equation with respect to x. What do you see to the left hand side is the term log y. Understand the difference, log y, but we have to differentiate it with respect to x. So the difference in the variable, so the derivative of log y just not be 1 upon y, but to be multiplied by dy by dx. This was all explained to you all in the previous session. So log y 1 upon y into dy by dx. And what do I see to the right hand side? If I read it, I get to know that I have sin x into log x, the product form. And if it is product form, then I know that the differentiation has to be using the product rule. So my derivative to the right hand side will be using product rule. The product rule therefore says the derivative will be the first function into the derivative of second, which we know is 1 upon x, plus the second function log x into the derivative of first is cos x. And if I know that I have completed the work of differentiation, then I just have to now see that I finally produce the value of dy by dx by rightly transferring the terms. Because the question stated is to find dy by dx. And if it is to find dy by dx, my value of dy by dx, if I write dy by dx will be equal to, this y therefore has to go to the other side. So y into bracket, if I just try to settle the terms correctly, then I may write the expression as sin x upon x plus log x into cos x. But don't forget, when presenting the final value of dy by dx, see that you have this y replaced by the actual value of y given to you. The actual value of y given being x raised to sin x, I will have to see that the same is used here in writing the final answer. So my dy by dx will be equal to x raised to sin x into bracket the whole expression which I have in the bracket, sin x upon x into log x into cos x. This completes your solution. So what we tackled here is a particular case wherein we had variable raised to variable form given for differentiation. With the knowledge of this, so if we have in this part learned how to differentiate variable raised to variable, then just to make you all aware also how to use this tactfully now for all other complex forms, I can tell you that you may have the case given as y equal to, no doubt, variable raised to variable, but you may find an example with this term given added to some other term. Say for instance, I modify the example now. This is the second example now given for differentiation to find dy by dx again. But the form has expanded now. Previously I had the single component of the type variable raised to variable. But what do I see now? I see that the similar term is given added to some other term. Now please remember that if the case is of this type, meaning not a unique form, but it is given added to some other form, then you have to be alert enough to remember that in this case the solution, immediate solution will not be on application of log, because it will not then enable you to apply log in a proper way. So for that reason, remember that if you see that your variable raised to variable form is given added or subtracted to some other form, then the first step in the solution will be to write the value of y as u plus v. What is u is what is v is, what I have done is I have just taken some notation for the first function and the second function, and this is must, this is must. Remember, if you directly start with applying log on both the sides, this log application on right hand side will not allow you then to take log of the first term and the log of the second term, because the property of logarithm doesn't work in that manner. So for that reason you need to be little alert in tackling these kind of cases. So if I have addition or subtraction, I will see that my solution, the first step in the solution is this. And therefore if y is equal to u plus v, how will I therefore get my final answer for dy by dx? It is my algebra which is there to help me. Algebra to tell me that your value of dy by dx therefore rightly will be du by dx plus dv by dx. So I know in advance how my value of dy by dx has to be finally constructed. So it is the addition therefore of two components, du by dx and dv by dx. So therefore now the entire job now is somehow to get the value of du by dx and dv by dx. Now where do I get du by dx from? Where do I get dv by dx from? Quite easy. So if I have to now find du by dx, what I will do is, I will go to the expression of u. What is u? I have taken u as x raised to sin x. How many functions are you handling now? I will say a single function. It is u equal to x raised to sin x. What kind of function is it? Variable raised to variable. And if it is variable raised to variable and a unique function for differentiation, what we have learned previously is not just by taking log on both the sides. See the part, the application which was difficult here at this particular level, it's become easy now here, because we have taken the form u separately. We are handling it as a single function now. So if it is a unique function, the application of log therefore is possible. So taking log on both the sides, and therefore I will have to then repeat the whole part which I tried for the previous case, because it is the same function which was taken. This will therefore enable me finding the answer for du by dx. What I will do next is, I will take my value v separately. What is v equal to? My value v function I know is 10x raised to sec x. Again, how many functions? Single function. Of what type? Variable raised to variable. And again, if it is a single function of variable raised to variable type, what comes next is applying log on both the sides. Again, the repetition of same kind of steps. And this will therefore enable you finding your answer for dv by dx. And what next then in finding dy by dx? It is just nothing but the value of du by dx will go here. Your value of dv by dx will go here, and this will complete your answer of dy by dx. So students, here is the concept. We call it derivative of functions in parametric form. Now by now you must have realized that after completing so much of content in the topic differentiation, we learnt about finding derivative of implicit function. We learned how to differentiate inverse trigonometric function. We also saw the examples called logarithmic differentiation. Now after comparing all these forms, like actually it must have clicked to your mind that there is no scope for creating any confusion there as far as methodologies are concerned. Like the method used for differentiating implicit function was totally different from what we did, because the steps at least, the method or the way how we write the solution was totally different from how it was for differentiation of inverse trigonometric function, isn't it? The methodology was totally different from what we did in logarithmic differentiation. So therefore, if you practice this, if you understand it very well and just keep on practicing it in the way we have done it, I'm quite sure there won't be any confusion in your mind, and you all will find the topic really easy. So here comes the next concept in sequence. We call it derivative of functions in parametric form. So again, my responsibility to explain to you the meaning of the term parametric form. Now what exactly is parametric form? To make it more easy, let me tell you. Suppose you know that usually all these whiles the equations were in the form x and y, the usual variables which we were using all this while. But suppose that, and then we also talked about explicit form, implicit form, wherein we tried to unite both the variables and try to frame one equation in terms of x and y. But imagine you found that there is no relation between the two variables x and y, but there is a third variable which is commonly related to these two variables. So meaning x and y are taken as two different variables. There is no connection between the two, but there is a third variable which is related to these two variables. Now what is this third variable? Let me consider it as say theta. Say for instance I have one definition given for x as cos theta, and I have the value of y defined as sin theta. Now don't you think that now we have somehow seen that there is a relation existing between x and y? It is all because of whom? It is all because of this new variable which I have taken. What is this new variable, third variable taken? It is theta. And this third variable which is taken, which you see is commonly related to the two variables x and y, this third variable theta is what we call as parameter. And therefore, the two equations which you see here, one for x, another for y, in terms of theta, these are called parametric equations. So therefore, now the concept, what if we are given some parametric equations? Again the question remaining the same. The question is to find dy by dx. So therefore see, moment we come across the new form, we learn the corresponding method of differentiating this new form. We came across a form called implicit form, and therefore we derived the method of differentiating implicit form. We saw the form called inverse trigonometric form, therefore we discussed the method of differentiating inverse trigonometric form. So what if we come up across parametric equation? There has to be some method of differentiating parametric equation and smoothly deriving the value of dy by dx. How do we do that? So that is what we are going to understand in this session today. So therefore, how exactly do we differentiate parametric equations, what we call as parametric differentiation? So therefore, let me first state one example here for you. Say for instance, if I am given x equal to say a cos theta and I am given y equal to a sin theta. Now these two are actually called parametric equations. What is the parameter used? Remember, a is a constant number. So it is stated further that a is a constant number and theta is the parameter. So this becomes a set of parametric equations. The question here is to find dy by dx. Now the exact method of differentiating parametric equation. Now what I have to do is, without forgetting that I have to finally conclude finding the value of dy by dx, the process of differentiation will begin in this manner. What I will do is, considering the first equation as x equal to a cos theta, realizing that the value x is defined in terms of parameter theta, I would first prefer differentiating x with respect to the variable in terms of which it is defined. So since x is defined in terms of theta, just to go the differentiation smoothly, I would first prefer differentiating x with respect to theta. Now what will be the corresponding differentiation? Quite easy, because I have the term defined in terms of theta. I know that I have to differentiate it with respect to theta. A being a constant will remain the same into the derivative of cos theta with respect to theta, as we all know, is minus sin theta. And thereby I manage smoothly deriving the value of dx by d theta as minus a sin theta. Fine. Half the job done. Next, taking the second form given, y equal to sin theta. Again realizing that defined in terms of parameter theta, I would again prefer differentiating this with respect to theta. So it is dy by d theta. See, dy by dx is far ahead. I have first found dx by d theta, and now I am trying to find out the value of dy by d theta. What do I do? So the value, I am differentiating this expression with respect to theta, knowing that a is constant. Derivative of sin theta with respect to theta, we very well know to be cos theta. Done. The second value found. Now please remember that these two values have to be correctly set or used in framing the required value of dy by dx. Now how do I do that? Now it is known that the value dy by dx can be written equal to dy by d theta divided by dx by d theta. Understand the form? So it is dy by dx is written equal to dy by d theta upon dx by d theta. What I have to simply do now is substitute the components which I have already calculated, found. So dy by d theta to be a cos theta divided by dx by d theta is minus a sin theta, and this will therefore enable me to cancel a and will help me in framing the required answer for dy by dx. As you see, because of this minus sign here, my value dy by dx therefore will be minus cot theta. Just to take another important example of the kind, let me just change the equations, the parametric equations. So I take the first one as x equal to a into theta minus sin theta, and I take the equation y as equal to a into 1 plus cos theta. Just to see another case, since we have already understood the method, let us try to apply the method here for solving this case. Again two parametric equations, again the parameter used is theta, the question remaining the same, to find dy by dx. I will be coming back to the same formula, but before that, as I know, I have to complete those two important parts, sections. One, finding the value of dx by d theta, and finding the value of dy by d theta. Now what will be my answer for dx by d theta here? Again I see the form a multiplied, so a being a constant will remain the same. I am differentiating the expression with respect to theta, so the derivative of theta with respect to theta is 1 minus derivative of sin theta with respect to theta we know is cos theta, and that's it, is my value of dx by d theta. I now proceed finding the answer for dy by d theta. What is my answer? A constant multiple, so will remain the same, bracket derivative of one constant is 0 and that of cos theta is minus sin theta. So I know that my dy by d theta value been calculated or been found as minus a sin theta. I just have to now place them rightly in this expression. So the answer for dy by dx will be equal to dy by d theta, as we have obtained, is minus a sin theta divided by the value a into 1 minus cos theta, thereby allowing me to cancel this, and so the value dy by dx is equal to minus sin theta upon 1 minus cos theta. Now if like in variations, now possible variations that you may also get to, like the questions, you may also find the cases wherein you are given the parametric equations and you are told to find the value of dy by dx at certain instance, like the question would be to find dy by dx at say theta equal to pi by 4. So if suppose I am given stated to find dy by dx at theta equal to pi by 4, the solution no doubt will have this whole content. But since the question it is asked to find dy by dx at the instant theta equal to pi by 4, that would only add few more steps to this solution. What I will then have to do is, if stated to find dy by dx at theta equal to pi by 4, I will just have to substitute theta equal to pi by 4 here, substitute the corresponding values, trigonometric values at the angle pi by 4, and derive the constant answer for dy by dx. That's it. Okay, so this is how we complete or I solve the examples on differentiation of parametric equations. And now coming to the last concept stated in the topic differentiation, we read it as second order derivative. Now since it is second order derivative, let me make you all understand how this particular concept is different from all that we were doing all this while. Now say for instance, what we were doing all this while was, if given any function y, say for instance I am given y equal to sin x, The question stated everywhere was to find the value of dy by dx. Now please remember that when I find dy by dx, this differentiation value is actually called the derivative of y of first order. So what we calculate dy by dx actually is the differentiation of first order. And therefore when it was y equal to sin x, we therefore knew that the first order derivative of sin x was cos x. So therefore, if I have any function defined as y equal to sin of x, or if I just try to generalize it, and if I write it as y equal to f of x, and if I talk about first order derivative of this function, then the first order derivative of the function can be denoted by dy by dx. Likewise, I can also denote it by f dash of x. It can be also denoted by, since it is the function denoted by y, the first order derivative of y can be also denoted by y1, and another notation, few other notations taken are like one may denoted also by y prime. So just to make you all aware about various notations taken for first order differentiation. So if you have any function and you have to write the first order derivative of this function, then you may write the derivative as dy by dx, you may denote it by f dash of x, you may denote it by y1, or you may also denote it by y prime. So all that we were talking all this while was up to first order differentiation. Now we come to the higher order. So second order differentiation, and that is why the concept stated as second order derivative. Now please remember that we would be now moving higher to the next derivative. So if I have to now go to the second order derivative, higher step, then just to make you all aware of the notations. So if this was all for first order derivative, now if I am asked to find the second order derivative, the notations which I would therefore prefer, or you may also find in the textbook taken, that the second order derivative therefore would be denoted by d square y by dx square. You will find it denoted by f double prime of x. It would be denoted by y2, or you may also find it denoted by y double prime. Now we are moving ahead finding the answers for these components. So what if asked to find the value of second order derivative? It's again quite easy. One example, say for instance I am given the function y equal to x cube plus 3x, and suppose the question is to find the value of d square y by dx square, meaning I have to find the value of second order derivative. Now how do I proceed finding the value of second order derivative? Now stepwise, if I have this as y, what I will do is I will differentiate the function with respect to x at the first level to find the value of first order derivative, isn't it? So the value of y, when differentiated at the first level, you get the first order derivative. Now what will be the first order derivative of this function? As we know, derivative of x cube is 3x square plus the derivative of 3x is 3. Now what we have found here is the first order derivative, but we are given to find second order derivative. Now how do I find second order derivative? First of all, the notation. I will denote it by d square y by dx square. And please remember or understand, now when it is the second order derivative, in sequence I can tell you, if first order derivative is the derivative of the given value of y, then by second order derivative we mean it is the derivative of the first order derivative. So therefore, when y is differentiated, we get dy by dx. And when dy by dx is differentiated, we get d square y by dx square. And the levels continue then. So therefore, if I have to write the value of d square y by dx square, it simply means it is going to be equal to the derivative of my first order derivative value. How much will be the answer? So 3 constant into, we know that derivative of x square is 2x plus that of the constant 3 is 0. And therefore, I get d square y by dx square as equal to 6x term. what I have calculated therefore is called the answer for second order derivative. Here is another important example taken. If we read the question, we get to know what exactly is asked in the question. We are given y equal to x cube plus 10x, a simple form, and the question is to find d square y by dx square. So therefore now, since discussed previously that if I have to reach to second order derivative, then it goes in sequence. So if this is my value of y, you differentiate it at the first level, you come to dy by dx, and this value of dy by dx, when it's differentiated again, we would reach to the value d square y by dx square. Let us try to do the same here. So therefore I would differentiate this expression with respect to x to derive the value of dy by dx. So when differentiated, dy by dx will be as derivative of x cube is 3x square plus the derivative of 10x we know is sec square of x, done with dy by dx. Since to find d square y by dx square, this expression of dy by dx has to be now newly differentiated with respect to x again. So I am now differentiating this newly obtained expression. This will give me my answer for d square y by dx square will be equal to, so when differentiating 3 into the derivative of x square known to be 2x plus, now when I have to differentiate the form sec square x, don't forget that your function sec square x is actually like sec x the whole square. So if I have to write the derivative of sec x the whole square, it has to be by using the formula of x square. Like how we know that derivative of x square is 2x, the derivative of sec x the whole square will be 2 sec x. Okay, so x square is 2x, so sec x the whole square is 2 sec x, but this in turn to be multiplied by the derivative of sec x, which we know is sec x into 10x. So done. If I know that I have obtained this by differentiating first order derivative, then this is going to be my value of d square y by dx square. If I just frame it correctly, then it is 6x plus 2 into sec square x into 10x. This has formed my expression for second order derivative. Now what other possible examples could be asked on this particular concept? Talking precisely about second order derivative. Say for instance, the important or the major examples, the cases which are asked on this particular part are the kind of examples. Say for instance, I am given y equal to sine inverse of x, and to show that 1 minus x square into d square y by dx square minus x into dy by dx equal to 0. The question stated, it is stated that I am given y equal to sine inverse of x, but the question asks is to show that I have to verify certain expression. The expression is 1 minus x square d square y by dx square minus x into dy by dx equal to 0. So something is given and something has to be evolved. Now how do I do this? Now in these cases, I would suggest a particular way or technique, steps for solving this kind of examples so that one can smoothly reach to the required expression. Now how exactly do we proceed? Given the phi value, so it is y equal to sine inverse of x. To what extent do I have to stretch my differentiation to? I get to know from the expression that I am required to derive, as it all talks in terms of dy by dx and also d square y by dx square. I know that my differentiation therefore has to complete or cross two levels of differentiation. First level will enable me find dy by dx, second level will enable me reach to d square y by dx square. So how do I go by? I have the value y, so therefore I would take the first level of differentiation. So I would prefer differentiating the expression with respect to x. Now what is the derivative obtained? So therefore if y, then dy by dx, as we know from the formulas learnt previously, the derivative of sine inverse x is 1 upon root 1 minus x square. Fine, one level of differentiation achieved. I have to go to the second level of differentiation. I know this well because that is where my final verification would be completed. So the first level completed, but I would suggest one thing here. If your value of dy by dx is in quotient form, numerator upon denominator, I would suggest always opt for cross multiplication before differentiating the expression. No matter, we have to differentiate it again because otherwise we won't be able to reach till d square y by dx square, but not at this level. Remove this hurdle. So cross multiplication. Do not keep the right hand side in the form p upon q. I would cross multiply. So this will give me the form root 1 minus x square into dy by dx as equal to 1. Next suggestion here is, again the next thing coming to my mind, I have to differentiate this, I know, but then, even then, I still see another hurdle in the equation. What is that? I see that there is root sign which I will have to take into account if differentiating at this particular level. I do not want any root sign to remain in the expression which I am going to differentiate later. So how do I remove that root sign? As we always do, removal of root is always by squaring the equation. I would prefer squaring the equation here. So if I square the equation, the next step obtained, the root sign will give me 1 minus x square. But not to confuse, I am squaring this part. So the square of this term will be dy by dx the whole square. Do not confuse this with d square y by dx square. D square y by dx square denotes the second order differentiation. What we are writing here is just the square of this component is equal to square of the right hand side is 1. So therefore, I now say that my equation is like free of any kind of hurdle. There is no p upon q form, there is no root form. I would now prefer differentiating this. So remove the hurdles and then take over the differentiation. Now my second level of differentiation will begin from this particular level. Now what exactly, how exactly do I differentiate this expression? Again, study the terms properly. See the right hand side. How are the terms to the left side? I see them in the form of product. First term into the second term. If so, if I have to differentiate it, certainly the product rule. Let me use the product rule. So the derivative first bracket into the second bracket. So the derivative will be the first term as it is into the derivative of the second term. How is the second term? It is in square form. Any term which is in square form like x square, we write the derivative as 2x. So if derivative of x square is 2x, then the derivative of dy by dx the whole square will be 2 dy by dx. 2 dy by dx. But I can't forget to multiply this by the derivative of dy by dx because I have used composite form. This is the composite form for differentiation. It is not rightly in the form x square. Some other term is there inside the bracket. So therefore, I cannot miss multiplying this by derivative of dy by dx. What is derivative of dy by dx? Is d square y by dx square. I have just finished multiplying with, I mean writing the first part of differentiation. First function into the derivative of second. To continue, plus second function dy by dx the whole square. So it is the second function into the derivative of first. Now what will be the derivative of the first function? 1, so 0 minus derivative of x square is 2x. So you understand that the derivative of this entire bracket will be minus 2x. So I multiply this by minus 2x equal to the derivative of right hand side being a pure constant number, the derivative right hand side will be 0. Have I now derived the required result? Just compare this equation with the form that you were told to derive. This is the form told to derive. Have you derived the required form? Just compare. Certainly not. Now what exactly do you see extra in the equation? If you notice very well, then it is this part 2 dy by dx and 2 dy by dx is common in the equation. I will cancel this common part throughout from the equation. So if I cancel the equation throughout, I mean cancel the component, common component 2 dy by dx from the equation, then that should give me 1 minus x square, 2 dy by dx is removed, into d square y by dx square, 2 dy by dx is removed, I write this as minus x into dy by dx equal to 0. Now if you see what we have derived finally is the expression that we were told to derive. So see systematically how we proceeded. The given value of y differentiated, but notice that it is in quotient form. So cross multiplication, notice that there was a root sign, so therefore opted for squaring the equation and then preferred differentiating the equation, and that only that common part when was removed we managed getting the required expression. Now students, with this we have actually discussed all the important concepts in the topic differentiation. But certainly what we try to explain to you all was just we just try to give you all the basic idea of the concept. Some important examples are discussed here, but you all know very well that the perfection can be gained only by when you can practice more examples of the kind. So therefore, with whatever that we have tried to explain to you in this session, with the knowledge of all the examples I tried to complete in this particular session, I would definitely suggest you all to try some more exercises of the kind to gain the perfection on in the topic differentiation. All the very best. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.